All right, so we're going to shift gears now for the rest of the course and then use the fundamentals which we have learned to apply to the case of specific radiation mechanisms. And the first one we're going to consider is Bremsstrahlung or free emission. This is the kind of emission you get in a plasma because of what are called Coulomb collisions. And these are basically collisions between plasma particles. So, you know, the most classical case is of an electron with a proton. And when I say collisions, don't imagine them being like two hard balls physically colliding, but think of them more as deflection of charges because of the electrostatic field of other charges, right? So I want you to have a picture where you have a proton and it has an electrostatic field, and an electron, you know, just happens to come by the proton just because of random thermal motions, let's say. And the electron is getting accelerated in the Coulomb field of the proton. And that acceleration, you know, is going to lead to emission, which means that overall the plasma is going to lose energy by radiating, and it's going to cool down, right? And so that's the kind of radiation we're going to talk about. And so you have the fundamental ideas already. You know how to calculate the dynamics of charges, and you know how to use the dynamics to get the acceleration, which you're going to plug in into Larmor's formula to calculate how much energy, electromagnetic energy, is emitted. And so you'll see eventually when we work through all of this that it's very hard to get a closed form solution which captures all of the physics which is involved here in a Coulomb collision. But you can get almost all the way to the right answer, you know, to a very good degree of approximation by making some simplifying assumptions. And we'll make that because, you know, it's used practically, but it's also because we don't want to get bogged down in the algebra and then lose sight of the physics involved here. So the first approximation we'll make is what is called as kind of a large impact collision kind of approximation. And the idea here is we are going to take, we're going to approximate that most of the relevant Coulomb collisions for the emission happen at very large impact parameters. So it's not that the electron is getting very close to the proton. It's kind of going about its trajectory and gets a small tug on its trajectory because of the Coulomb potential of the proton. And so what does it look like? Imagine that every proton has like an annulus around it, as I've shown here. And let's say that's an infinitesimally thin annulus with radius of b, which I'm going to call the impact parameter. And it has some tiny width dB, right? And so what I'm trying to say is that when an electron is moving through this gas, it kind of sees each one of these protons as these kind of circular annuli, okay, of radius b. That would be all the collisions with impact parameter b with the proton, right? So if you just calculate, you know, what is kind of the rate of these kind of collisions as the electron is going through. So dn by ds, number of collisions per unit length it travels. You know from the same kind of arguments which we had when we calculated the absorption coefficient, right? So n is the volume density of plasma particles, and the area, cross-sectional area presented by a single particle is 2 pi b times dB. And so you can see that there's just more area at larger impact parameters. So most of the collisions are going to be at large impact parameters. They're not going to be at small impact parameters. Now, that doesn't mean that this assumption of large impact parameter collisions is completely justified. It depends on what you're trying to calculate. This just shows that there are just more collisions at large impact parameters. Of course, you need to figure out whether in terms of the energy emitted, it's the larger impact collisions which are more important or the small impact collisions which are more important. But anyway, we'll get to that eventually when we actually calculate the energy emitted, and we can see which collisions, which range of values of B are going to be the most important for the energy emitted. Okay, so for now, just take this as a given that most collisions are, you know, large impact parameters, and those are the important ones. And those are the ones we are going to study, and that's going to lead us to some simplifying assumptions. So what kind of simplifying assumptions can we make? Well, let's just qualitatively look at the trajectory of an electron which is passing by a proton, okay? And its closest approach is at a distance b from the proton. Now, the Coulomb force which the electron is going to experience is shown by these arrows here. So when the electron is kind of far away, the force is small because the distance is large, and the force is going to be the largest when, you know, it's at its closest impact at a distance of b, and the direction of the force is always pointed towards the scattering center. Okay, and in this case, I've just assumed that the proton is so massive that it essentially remains fixed, and the electron is, you know, 2000 times less massive, so it is the one which is getting accelerated. The acceleration, the actual movement in the position of the proton is quite small. It's just fixed because it's massive. Now, you don't have to do it. You can actually work in the center of mass frame of the two charges, right? And then you can actually do all your calculations in that frame. Again, it just complicates the algebra a little bit. So I don't want to directly go into the center of mass frame. Maybe we'll do a problem on that in case of an electron positron collision, let's say. But for now, let's just assume that the electron has a trajectory which is only slightly jiggled by the Coulomb force, and it's at a large impact parameter. So if you just look at the acceleration of the electron, let's look at the x component, which is along the trajectory here. At large distances, of course, the acceleration has to go to 0, and the acceleration is going to flip sign, right? It's going to flip sign right at this point of conjunction where, you know, the acceleration is purely along the y-axis. And so you're going to have some curve that looks like this, where the acceleration is 0 at the two ends, and then it crosses 0. It's kind of an odd function. If you look at the y acceleration, again, it has to go to 0 at large distances, but it kind of has a peak at this point here of closest impact. And so at the, you know, it's along the negative y-axis, the way I've drawn here. And so you get kind of a peaked function like this. And so these are the accelerations which we need to calculate. And once we have done it, you know, we are almost done, right? You know how to calculate the energy radiated given the acceleration. Okay, so what does the force equation look like? Let's just write the force equation. Again, we are making the assumption here that the electron almost moves on a straight trajectory, right? And so, you know, if you want to do it properly, you'll actually have to calculate the trajectory of the electron, and the distance between the electron and proton don't vary exactly as if it's going in a straight line. But we're not going to do all that. We're just going to say this is a high impact parameter collision. The electron almost goes along a straight line. So what does the force look like as a function of time? Well, the y component of the force is going to be determined by just the Coulomb potential times the charge, right? So the charge is q of the electron. The Coulomb potential is just going to be q divided by the distance square. But we just need the y component, right? So we need to take the component of the force along the y-axis. So you need to take a direction cosine along the y-axis, which is going to be b divided by the distance, right? So you have distance square, and then you have another factor of distance, which is square root of b squared plus v squared t squared. So the whole thing put together gives you 3/2 power of the distance in the denominator. Square of the distance, sorry, in the denominator. And, you know, the distance is quite easy. You just assume that the electron velocity isn't changing much. So the distance is just going to be the, you know, you can just use this right angle triangle. It's just going to be the Pythagorean, the hypotenuse, sorry, of the triangle. Okay, so that's the y component. So what about the x component? Well, it's the same thing. Instead of b in the direction cosine here, you're going to have v times t, which is the x displacement. Okay, so instead of the y displacement, you have the x displacement. And you can see that you get an odd function here, you get an even function here. What do these functions look like? Well, you know, you can kind of do some basic algebra to get some intuition here. This function, you can calculate its extrema, right? You can just take derivative, set it to 0. You get an this function is simpler. The extrema just happens in this case when t equal to 0, right? And so you just get q squared by v squared. You can do the same here, just take the derivative, set it to 0, you get the extrema. It kind of happens at vt of the order of b in this case, and the extrema is comparable. You know, there's some factor here which I've left out, but it's going to be of the order q squared by b squared. You can pause the video and actually do the algebra yourself. So the idea being that these two factors have the same extrema, which means that the heights here are kind of similar, okay? And the scale over which the interaction is important is given roughly by b, okay? So the width of this is roughly of the order B, and the same here. The width of this is going to be roughly order B, which means that the whole B times T, B divided by the velocity, right? So I have time here, not displacement. So anyway, the idea being that you can model this collision as some kind of an event, okay, a singular event of a short duration, and the duration is just given by the time it takes for the electron with its velocity v to cross a distance given by b. Okay, so that's kind of the time scale of the collision. Now, we're going to now make the next approximation, which is to say that the electron is not moving relativistically. Okay, so if the electron is not relativistic, so if you go back to the previous lectures which we did, we said that, well, then we can use the dipole approximation. And what does it mean? Well, it means that we don't worry about the different retardations at different positions on this trajectory. We take one common retardation for this entire event, which is the Coulomb collision, right? And so when you do that, then this sign flip is now important, because when you add the electric fields and don't take into account the different retardations at different points of the trajectory, this is going to average to zero, right? This is going to lead to an electric field that averages to zero. So it's really the y component of the acceleration which is creating the emission, just because, you know, this is a function which is an odd function, right? And so again, so what ends up happening is, because I'm not putting in different retardations at different points on this curve, when I actually calculate the total electric field, some kind of a time integrated quantity, then the emission which happens over here when it is at a peak here compared to when it is at a negative peak here, these two are going to have electric fields in opposing directions. So if I'm looking only for so-called low frequency emission, right? So I'm not looking at temporal structure in the emission on the time scale of the collision. I'm only looking for low frequencies. So I'm only looking for, I'm only looking at frequencies which are so low that, you know, you kind of get an averaging of these two opposing peaks. And so you get a zero electric field. So you only have to worry about the y component in the dipole approximation at low frequencies. Okay, so this is not just dipole approximation, it is also at lower frequencies. Okay, so what do you get? Well, you just get the acceleration is same as the force divided by mass. Everything is non-relativistic here. That's simple. And so now you have all the prescription, right, to actually calculate the fields in the dipole approximation. Okay, so you can literally take the dipole moment and then plug it into a formula which we had before. So the electric dipole moment here is q times the y position of the electron, right? And so the second derivative of dipole moment is what you need, which is proportional to acceleration, and then you already have an expression for that. Now, if you go back to our previous lectures, we derived the electric field in the dipole approximation as a function of the acceleration of the dipole moment, d double dot, and that's the equation. You can go back to your notes to check on this. So you plug all of that in and you get electric field as a function of time, okay? Now, notice what I said about low frequencies, right? So in reality, this x component of acceleration is going to give you an electric field, which is also an odd function, right? It's going to go up and then suddenly down in the other direction. Now, if you look at very low frequencies, this up and down is going to get averaged, right? So how low is low? Well, it's low enough that you're looking at frequencies that are lower than 1 over the time scale of collision, right? And what's the time scale of collision? It's b divided by v. So when you're looking at very low frequencies, then you don't really have to take into account the x component of the acceleration, because that field will average to zero. It's only the very high frequencies where you will actually see an effect with the x component of the acceleration. Okay, so under the dipole approximation, you can now write it as a spectrum, right? The frequencies are important. And so, you know, we want to actually look at the spectrum of emission, because we now know qualitatively already that there is a distinction between low and high frequencies in the way we evaluate the spectrum. Okay, so what does the spectrum look like? Well, that's just the Fourier transform of the time domain electric field. Again, this is all repetitive, right? We actually derived an expression to directly go to the spectrum from the Fourier transform of the dipole moment. Anyhow, you can plug all of that in. And then you can say, well, okay, so what does the spectrum look like? Again, in the low frequency approximation, right? So in the end, what you essentially have to do is a Fourier transform of this quantity here. This is the only time variable quantity. The others are not time variable, okay? And the question becomes, well, what's the Fourier transform of this? Well, you can actually do this in closed form. These are actually related to Bessel functions. But let's just do a more qualitative thing here, a kind of semi-quantitative thing. Notice that this function is just given by that impulsive thing along the y direction, and it has a significant value only on a time scale given by b by v, right? Impact parameter divided by the velocity. So if I now choose a frequency which is far, far less than v by b, the inverse of the time scale, then I have a scenario where this function here, when it has significant values, e to the power I omega t is, I omega t is very close to 0, right? So e to the power I omega t is almost equal to 1 when omega is too small. How small is too small? Well, it has to be smaller than the inverse width of this curve, right? So that's basically v by b. So what happens in that case? Well, you can just place e to the power I omega t equal to 1, and this you can just do in closed form, okay? So I've just done it here. You can pause the video and check it out. You can solve this integral in closed form and you get 2 by vb square. Okay, so you plug that in and you're done. You basically get the Fourier transform of the electric field, and you already know how to calculate the Poynting flux and all of those things from the Fourier domain electric field, right? We've done this before. So I'll just, I'm not going to write the final expressions because you know how to do it. Maybe we'll do it in class as a problem. Okay, and if omega is far, far greater than v by b, then notice what's happening. That means that this exponential here is varying way more rapidly than this curve here. That's what that condition means, which means that you have a rapidly oscillating quantity inside this envelope of that curve, right? And so all of that is going to average to 0, because if you just average a rapidly oscillating quantity, you're going to get 0. So which means that the electric field is going to be 0 when omega far, far greater than v by b. And again, this hits at the approximation we have made, right? So we've made this approximation where we're looking at low frequencies, and at higher frequencies, the emission is going to be very small, and we've just made it identical equal to 0 in this approximation. Now again, you can calculate what is the amount of energy emitted. Well, this is basically the Poynting theorem in Fourier domain, right? That's energy emitted per unit frequency per unit area. That's just Poynting theorem in Fourier domain. We did this before. And then, you can write unit area as per unit solid angle times r square. R square cancels out on both sides. R naught, I've written it as r naught here, which is the distance from the Coulomb collisions to the observer. And again, you can integrate over the solid angle. Sine square theta integrated over solid angle is, I believe, 8 pi by 3. I think we did this several times before too. And so you get the final expression here, which is the amount of energy emitted per unit frequency in 1 Coulomb collision. So you take the aggregate effect of 1 Coulomb collision, and then you say, okay, how much energy is emitted at different frequencies? The answer is, well, for frequencies far, far less than v by b, that's the energy emitted, and it goes to 0 rapidly for frequencies far, far greater than v by b. Okay, so notice that this expression doesn't depend on frequency at all. So you actually have a flat spectrum, which means that at very low frequencies, in each frequency interval, you get an equal amount of emission, right? The amount of emission per unit frequency doesn't depend on the frequency itself. So you get kind of a flat spectrum, which rapidly cuts off, okay? Just as an aside, it turns out that you can actually calculate the actual form there in closed form. So that integral here is what we approximated as low frequency limit, high frequency limit. Well, it turns out that this is a very common integral. They're related to Bessel functions. So I'll just note that similarity here. Just first thing you notice is that's an even function. And so if I use Euler's formula and write this as, cos of omega t, I times sine of omega t, well, the sine term goes to 0, right? Because that's an odd function. This is an even function. That integral is going to go to 0. So you only have to worry about cosine, which is also an even function. And so you have an integral which is all an even function. So it's 2 times integral 0 to infinity. You can write this in a standard form, which I've done here. You can pause this and then check the algebra here, but you can write it in this standard form. And this is basically this integral is going to end up, the standard form is that it's going to end up being a modified Bessel function of the second kind, which is the usual notation is k here of order 1. And that's what it's going to end up being. Now, if you remember, I is usually I of 1 would be the modified Bessel function of the first kind, and those are exponentially increasing functions of their argument, and the ones of the second kind are exponentially decaying functions of their argument. Okay, so you can plug all of that together, and then instead of that a low and high frequency thing, you just get a smooth function which at low frequencies, right? And so the argument here is the same as the factor outside. So if you just take these two together and then plot them, then k1 itself goes to infinity at low frequencies, but k1 times the argument goes to 1. At very high frequencies, this is exponentially damped, so it kind of goes to 0 very rapidly. And then when that argument is of the order 1, that factor here is roughly of the order half. So instead of a step function, you have a more smoothly varying function. So I just want to put this out here because you might encounter expressions for Bremsstrahlung emissivity which have this Bessel function. So I just don't want you to get confused about where on earth this Bessel function came from. Okay, so that's how you basically evaluate the energy or the spectrum, the power emitted or the spectrum of Bremsstrahlung. Now, that was for a single collision. So you can ask the question, well, what happens if you have like a realistic medium? Well, again, if you look at the expression for a single collision, then you have velocity here and impact parameter here. So, right. So if I now tell you, okay, let's assume it's a thermal medium, right? So you know what the distribution of velocities are, right? I have given you a prescription for the velocity distribution. And now you can use that to calculate what is the prescription for the impact parameter distribution, right? So you basically would have to take this expression, which is for a single collision, and kind of do an average, like integrate over the velocity distribution and the impact parameter distributions to get the emissivity of a medium, right? So you can do that, and we'll do some problems of that sort in class. We'll just take a thermal medium because you'll end up getting expressions which are just easy to integrate. In that case. So maybe we'll do a problem like that to find the emissivity of Bremsstrahlung emission in a thermal medium in class. But essentially all you need to know is, you go to the first principles, you calculate the dynamics of the charge, you figure out the acceleration, maybe you need to do some simplifying assumptions to get things in closed form. Not just in closed form, but also to get expressions which are good enough for realistic circumstances. And then once you've made those approximations, you need to calculate what would be your expression of interest, like let's say amount of energy emitted per unit frequency in this case. Sorry, this has to be omega, I think it's per unit frequency, or the Poynting vector or whatever you're after, right? You do it for one particular particle. And then once you have a prescription for the dynamics of the ensemble of a medium, then you do the necessary integrations over velocity or impact parameters to get it for a realistic distribution. So that's going to be the basic prescription for any emission mechanism. You start with a single particle emitting, and then you expand that out to the whole medium.